Hello, Math 201. Today we start section 3.2, the derivative as a function. So far we've defined the derivative at a point, right? And this is the slope of the tangent line at x equals a. So in particular, f prime of a is a number, and that number is the slope of the tangent line, right? How steep it is, or positive, negative. But what happens as a changes, right? If we plug in different numbers for a, what happens to this derivative? So to kind of illustrate that, here's a picture. Here's a function, f of x, and we take the derivative here at a, the slope is positive, and so the instantaneous rate of change of the derivative is positive, so it's up and to the right. At this point b, the slope is 0, the instantaneous rate of change is the derivative at b, it's 0, and then on the right, the derivative is negative because it's down and to the right at this point c. And so the derivative itself can be thought of as a function. For any x, we can calculate f prime of x. Thus, f prime of x is a function, right? It is something that you plug in a value x and it will spit out a number. And so this function, the derivative function, will tell you what the slope is at any point, and it itself is a function. And so here, x is a variable, not a number. So f prime of x is a function. When we write f prime of a, that's a number, meaning a is a particularly chosen value. X is a variable. So you can plug in x and then it will become a number. And so the derivative function, we're going to use this definition, but you can also equivalently use the other one, x minus x prime or whatever, and it'll give you the same, but we're going to do the h limit definition. And the derivative of a function is the following function where x is a variable. So f prime of x is the lim as h approaches 0 of f of x plus h minus f of x over h, provided this limit exists and that x is in the domain of f. If f prime of x exists, we say that f is differentiable at x. If f is differentiable at every point on an open interval, we say that f is differentiable on that interval. So the process to go from a function to the derivative, so from f to f prime, is called differentiation. To differentiate means to take the derivative, which means to take this limit. And so if we want to find the derivative of a function, which will be a function that tells us the slope at any given point, that's f prime of x. And so let's do an example. So let f of x be the following function. How can we find its derivative function? Well, remember, by definition, f prime of x is equal to the limit as h approaches 0 of f of x plus h. And so maybe we should do those first. So what is f of x plus h? If I plug in x plus h into this function, what is it? It's negative x plus h squared plus 6 times x plus h, which if I FOIL that all out, it'll be negative x squared plus 2xh plus h squared, and then plus 6x plus 6h. Plugging that in, I get negative x squared by distributing this, negative 2xh minus h squared, and then plus 6x plus 6h, because that's f of x plus h, right? Let me do this in color. So that's f of x plus h, and then minus f of x, which is negative x squared plus 6x, all over h. So that limit. And if you just tried plugging in h right now, you'd notice that you're going to get 0, 0, 0, and then minus x squared and 6x plus x squared minus 6x. And so you'll get 0 over 0. And so we have to simplify it a little bit. And so if we simplify some things, that's going to cancel with that. That's going to cancel with that, because you have to distribute that minus sign to both. And actually, let me do that. So this is the limit as h approaches 0. And this will become minus x squared minus 2xh minus h squared plus 6x plus 6h, and then plus x squared minus 6x, because we distributed that to that, both of those, all over h. And now some things will cancel. That will cancel with that. That will cancel with that. And now the h's will cancel with that because all that's left is h. And so we get the limit as h approaches 0 of minus 2x plus, minus 2x minus h plus 6. And if you plug in h equals 0, you get minus 2x plus 6. So f prime of x, the derivative function is negative 2x plus 6. So given that this was our original function, that polynomial, this equation tells us the slope at any point if I plug in x. And so now instead of having to always do the limit formula every time, we can do it once and for all and get a general formula for the derivative. And now we can just plug in numbers into that. And so that's what the derivative function is. And so let's take a real quick aside to talk about notation. So if we let y equals f of x be a function, then the prime notation, y prime of x, is sometimes what you'll see, y prime of x. It's the same thing as f prime of x. They both mean the derivative of f of x. And sometimes you'll see this f of x prime. So taking the prime of it means just take the derivative. That's the prime notation, or the Newton's notation. Sometimes we're going to see the Leibniz notation. And so d dx of f of x means take the derivative with respect to x of a function, or sometimes you'll see it as dy dx or df dx. They all mean derivative of f of x. All three of these just mean take the derivative of x. And so these are how we write for a function. How about at a value, y prime of a and f prime of a, d dx evaluated at x equals a of f of x, or dy dx evaluated at x equals a. That's the notation. Those all mean the derivative of f of x evaluated at x equals a. And so we'll see all these notations. In particular, this Leibniz notation or this Leibniz notation are useful in certain circumstances. But most of the time, we'll probably use the prime notation. But I want you to be able to know both. And so they all mean the same thing. These mean derivative of f of x, these mean derivative of f of x, and these all mean derivative of f of x when you evaluate it at a point, x equals a. So let's do another example. Let's find d dx of the square root of x, which is the same thing as f prime of x, where f of x is the square root of x. So by definition, f prime of x is the limit as h approaches 0. H approaches 0 of the square root of x plus h, because that's f of x plus h, minus the square root of x, because that's f of x, all over h. And so again, because you have to plug, if you plug in square root of, if you plug in h equals 0, you're going to get 0 over 0. So we need to multiply by the conjugate. And so let me just do that in red. So multiply by the conjugate, square root of x plus h, plus square root of x, all over square root of x plus h, plus square root of x. That way the top will simplify really nice. It will become x plus h minus x all over, and this is the limit as h approaches 0, and it will become h times square root of x plus h plus square root of x. Then something else really nice happens. That x will cancel with that x, and you just get an h on top. And so the h cancels with that h. And so what does this become? This just becomes the limit as h approaches 0 of 1 over square root of x plus h plus square root of x. Now you can plug in h equals 0, and this becomes 1 over 2 square root x. Another way you could write this is 1/2 and then x to the negative 1/2 power. Those are all equivalent. And so that is the derivative. So the derivative of the square root function. So maybe I'll write it over here. So if f of x equals x to the 1/2, then the derivative function f prime of x is positive 1/2 x to the minus 1/2. So that's the rule we just got from this. And we derived it using the formula. And so that is how we get the derivative. For the rest of this lecture, I'm going to talk about graphs of derivatives. So to calculate derivatives right now, the only thing we have is this the formula. And so I will say that this is very tedious and cumbersome, and we're going to find a better way in the next couple sections. But for now, this is how we actually have to, this is how we calculate a derivative. So now I want to take a quick break from that and talk about graphs of derivatives. So if f prime is the derivative of f, because its graph is derived from f, that's kind of where the term derivatives come from. It's derived from the function. And so the key idea is this: the value of f prime, so what this number it spits out at a given x value, is the slope of f at the same x value, because that's the slope of the tangent line, right? So when we say slope of f, I mean slope of the tangent line. So here's an example. Let's say that this is my function f. I'm given this kind of piecewise, kind of a spiky, like mountain-like function, where the slopes are all, they're constant slopes. And I want to graph the derivative from this. For the x values from here to here, and maybe I'll do these in color actually. So let me do this first one in orange. So for these x values from -5 to -2, the slopes are all the same along here. And the slope is always going to be down 1 over 1. So 1, 1. And so the derivative, so f prime of x here for these x values is going to be -1 because the slope is down 1 over 1, right? So the slope is -1. And so how do we graph that? So if you go, actually, I don't really like this color. Let me pick a different color. You can't really see this color very well. Let's do purple. So from here, so for all the points along here, the slope of the tangent line is just the same thing as the slope of the line because it's a line. And so the slope goes down 1 over 1, so -1, 1. And so f prime of x is equal to -1 for the x values between -5 and -2. So along that, the value, and so how do I graph that? So I would come to the, and maybe do this in black actually. So let me do this in black. So let me add a line here. So this is the line -1. So along that line, the slope has the derivative has the following value. It's -1. It's not really going to actually be defined there because it doesn't really have a slope. There's no tangent line at that point, right? There's no one tangent line, so it's going to be an open hole there. And then for the values between -2 and 0, the slope goes up like that. And so the slope is up 1 over 1. And so f prime of x for these values is going to be 1. The slope is 1. And so let me actually move this. That's kind of in the bad spot. And so for there, I'm going to draw an open circle there, and it'll go up like this, and it'll be an open circle there because it does not take a value there or there because there is no slope of a tangent line there. And then for this little bit, the slope is always -1. So for this little bit, so from this x value to this x value, the slope is -1, right? It goes down 1 over 1. Oh, sorry, it goes down 1 over 2. So it's actually not -1. It's -1, 2. And so f prime of x in this, for these x values, is going to be -1/2. So -1/2 would be right here. And so I'm going to draw an open circle there, and I'll go all the way over and like that. And so this right here, that is f prime of x. F prime of x is that from between -5 and -2, the slope of the original function was -1. So the value of this function is -1. This derivative is going to be -1. Between x equals -2 and 0, the slope was +1. So the value of the derivative function is +1. And then between x equals 0 and x equals 5, and I guess technically it is defined over here, right? At that point, it does exist at that point, right? The slope of the tangent line. So it's fine. We can put a filled in dot there and there. But right here, there's no tangent line because there's no one way to draw a tangent line there. But for all the points here, you can do that. And the slope is -1/2. So the value down here is -1/2. And so that's the idea, is from given a function, I can plot what its derivative function will look like, because the derivative function's value is just what the slope is on the original function. Okay, and so for sake of time, I'm going to just do these other ones a little bit quicker. So let's say I have this graph g of x. This is in black right here. Then to sketch a graph of its derivative, and because there's no values here, I can only give a sketch, won't be exact. The idea is that from -4 to -3, for those x values, the slope is positive, but they're getting less positive as we move to the right, and then they become 0. So they're positive, high positive, and then become less positive, and then go to 0. And it's 0 at x equals -3. And then for this next little stretch, the slopes are all negative. They're less negative, and then more negative in the middle, and then less negative. So less negative, more negative in the middle, and then less negative. So that's why it looks like that. And then it hits 0 again. And then from -1 to 1, it does the same thing, but opposite, right? It's positive, less positive, more positive in the middle, and then less positive. So less positive to more positive to less positive, back to 0. And then from 0 on, the slopes are small and then become really, really negative. And so it goes off like that. And so the way I would plot this is I would find all the points where the derivative is 0. So where the tangent line is horizontal. And then I would plot those x values first. And then the slope is positive here, so I need to be above the x-axis here. The slope is negative here, so I need to be below the x-axis here. It's positive here, so I need to be above the x-axis here, and then it's negative here. And so that's how I get something like that. And so this would be kind of a sketch of the derivative graph. And for those of you who are familiar, this with polynomials, this is kind of a quadratic graph, right? Because it has multiple ups and downs. So, and it's an even polynomial because they both go in the same direction. And it's kind of a fourth degree polynomial because it has this kind of up and downness to it. And then its derivative looks like a cubic. And that's not by accident, because it actually turns out that the derivative of a fourth degree polynomial is a third degree polynomial. And then here's another example with some asymptotes. And so again, what I kind of would do is I would find where the derivative is 0. And it seems there's only one real spot where the derivative is 0. Here, it seems like the derivative is getting really close to 0. And so it's kind of asymptotic behavior. And the slope blows up and goes to -infinity. So they're really small negative and then really, really big negative. So it looks like that. And it's going to have the same asymptote as this function because it's not defined where the function's not defined. And then for the middle part, these are really, really big negative slopes, 0, and then really, really big positive slopes. And so really big negative slopes to 0 to really big positive slopes. And then finally, for this asymptote, it's really, really big negative slopes, and then they taper to 0. So really big negative slopes getting close to 0. And so that's what the derivative of this function will look like, because every point on here has is representing the slope of this function right here. So the fact that this number is close to 0 means the slope at this number is close to 0. The fact that this number is 0 tells us that the derivative or the slope of the tangent line is 0 right here. And then we'll talk about how continuity and derivatives relate. And so this is an important theorem. If f is differentiable at a, meaning the derivative exists, then it's continuous. So that means that there's no holes, there's no gaps. It means that the limit is equal to the function value. And then the opposite is not true. You can be continuous and not differentiable. So the opposite, that is not true in general. But the contrapositive is true. If f is not continuous, then it cannot be differentiable. And so if there's a hole or there's a jump, then there's no way it's going to be differentiable. But continuity does not imply differentiable. Some continuous but not differentiable functions. So here's some examples. So here's a continuous function. It goes like this, and then it streaks like a corner. This function is continuous. I didn't have to pick up my pencil, and the function value is defined there, but the slopes kind of abruptly change. The other way you could do is you have a vertical tangent line. So the square root of absolute value of x, it comes in, and then it abruptly change. And so there's no derivative at that point. Or you could have a horizontal or a vertical tangent line like this. And so the derivative does not exist at that point because it's infinity. And so even though the limit exists, and the derivatives are getting really, really positive, and then even though the derivatives are they're both going to positive infinity. So the slope's getting really positive and they're really, really positive and go to and get smaller. And so you can have these things that are continuous but not differentiable. And so when a function is not, when is a function not differentiable? It's not continuous. It has a corner, so that's like this, a corner, or it has a vertical tangent line. So this is a vertical tangent line. So it kind of becomes really, it comes straight up and down at a certain point. And so that's when it's not differentiable. And so let's do one final example with some continuity. So let's say we have this non-continuous function. So it's open there, it kind of has a corner and then goes, has a hole there and goes. So from between -4 and -2, the slope looks like it's about 1. But then we will not include that point. We won't include that point because the function's not continuous there. So it's definitely not differentiable there. So there's no derivative there. But then really, really close on the other side, as we approach it from the left, it seems like it's getting really, really close to 0. And so we'd say it's 0, and then it gets really, really big in the negative direction because it's getting really, really, the slopes are becoming closer and closer to straight up and down, which is technically infinity slope, and they're in the negative direction. And then coming from the right, they're going to be really, really big positive slopes until it kind of tapers off here and goes to 0, but it doesn't actually include that point because the function does not have a value there. And then the derivatives, we move to the right, they're getting more and more negative until it kind of gets this asymptotic thing at 4, and we'll go to that. And so this would be how we graph the derivative of that function. All right, that should be all you need for section 3.2. I'll see you guys for 3.3 next.